So here, let me talk through, I guess, the final of this quiz here. Let W be a subspace. Prove that W perp is a subspace. We have to check that 0 is in W perp. And that means, is this true? Is 0 something you could put in for V? Is it true that 0 dot W always equals what? Yeah, when you dot product 0 with another vector, you get W for all W in W. So that says to me that 0 is in W perp. Okay, so that's interesting. For the next piece, question, Jake?
No, I was going to say.
Okay.
So you have to prove that C, I said that C, if my other vector was just X.
Okay.
So I said Cx dot CW has to be 0.
So I'm just going to say W.
W, yeah.
Cx dot W is 0 if X dot W is 0, right? Because we're saying that suppose X is in W perp. Is it true that Cx dot W is 0? Well, yeah, because if X dot W is 0, then you get it. That's right. So maybe kind of this kind of thing. This is true because X is in W perp. And so basically what Jake just did for us is he proved that it's closed under scalar multiplication. Right. Okay. So maybe right here, that takes care of scalar multiplication. So maybe the last thing we have to check now would be addition, right? So for the last one, let's suppose U and V are in W perp. And let's show that U plus V is in W perp. Well, how do we do that? We take U plus V dot W, but that equals U dot W plus V dot W, right? And we know that each of these is 0 because of the given. So we get 0 again for any W in W. And this shows that it's closed under addition. And so all this work shows that if you have a subspace W, there's another kind of automatic subspace that comes with it, W perp. Okay? And it's called, again, the orthogonal complement, W perp. Okay? Now, there was a quiz question. I asked you guys quiz question 2. I had another quiz question too I almost asked. I wonder if you guys would have gotten it. Here was the question that I thought about asking. The question would have been this. What did you learn about the null space of A? Did you guys learn anything about the null space of A in this section? Jake?
I believe it was, I forget it was row or column space. I think it's row. The orthogonal complement of the row space.
Okay, right. It's the orthogonal complement of the row space, right? So I didn't know if that was a fair question or not. I decided this one would be better. Okay, but yes, it turns out that it is the orthogonal complement of the row space. Okay, And so your book has this picture of the 4 fundamental subspaces. And I think I'll draw that for you in a little bit here. But anyways, let's get these quizzes turned in. Tell you what, so again, here's my matrix 1, 1, 2, 2, 3, 3. It's a map from R2 to R3. The row space is the span of 1, 1, so that's the blue line. The null space, if you work it out, you get y equals negative x is the null space, and you can see that those are orthogonal, right? Those are perpendicular. You guys see that? That's a nice picture. That's a nice picture. Okay, over in R3, in the world of R3, I might ask you guys, what can we say about the column space of A? Because it lives in R3. The column space of A would be the span of what? What would be a basis of the column space? 1, 2, 3. 1, 2, 3. Now where is 1, 2, 3? Let me see. Here's 1, 2, and then 3. So if I drew this kind of box, I could say that the column space of A comes up through this point of the box and also through the origin. This is somehow the column space of A. And the column space of A is one-dimensional, and that means that its orthogonal complement has to be how many dimensions? 2, right. So it turns out that the orthogonal complement, all right, which I'll draw now, would be a 2-dimensional, it would be a plane. So maybe you can picture this, I'm trying. This plane you could think of as the column space of a perp. But it turns out that what that is, that's the null space of A transpose. The null space of A transpose. And so these are called the 4 fundamental subspaces. Okay? So basically, when I say, what did you learn about the null space of A? What I hoped you learn is that it's one of the 4 fundamental subspaces. But maybe the last thing to show you here, when I say that the null space of A transpose is the complement of the column space, let's take a quick look at that, okay, picture-wise. Let me zoom out a little bit. Ooh, I think I zoomed in. So, again, A transpose would be the matrix, let's see, 1, 1, 2, 2, 3, 3, right? This is 3 by 2, so it's a map back from R3 to R2, right? It goes back. And if I said to you guys, find the null space of A transpose, right? If I said, find the null space of A transpose, well, what would you do? You would do the same thing. You reduce row echelon form. So you would have 1, 2, 3, 0, 0, 0, 0, 0. How many free variables would you get this time? You get 2, and that's why you get a plane. What would the plane be? Well, the plane would be x plus 2y plus 3z equals 0. And if I asked you guys, hey, what do you know about that plane? You might say, oh, I know the normal vector. The normal vector for that plane is 1, 2, 3, and that's why the column space is orthogonal to the null space. You guys see that?
So which way is that line going?
So the line is supposed to be coming out of the paper. You know? So yeah, I got it like this because I have that at a slant. But yeah, if you really wanted to see it, here's the plane and it's coming out at you. Yeah. See that?
Wouldn't it be orthogonal?
It's orthogonal to the plane. That's the point. Yeah.
Which plane?
The plane that is the null space
I thought that was
of a transpose. What?
I thought that was a line, not a plane.
Which one? The null space of A is a line, but the null space of A transpose ends up being a plane. And we showed that down here because you'll notice that when we did the reducer row echelon of A transpose, there were two free variables. Okay?
Okay.
So yeah, you don't have to have the same number of dimensions, and in this example you don't, right? A and A transpose behave very differently. A is a map from R2 to R3, but what's A transpose? It's a map back from R3 to R2. You guys see that? Mm-hmm. Okay. So that's some of the main ideas for today, I would say. Yeah, so I think I'm going to reproduce, well, yeah, something like that. Okay, so let's do on the screen. These are going to be some notes about the orthogonal decomposition theorem. So let's say that this is W. That's a subspace. Okay. And let's say that this is my vector V. Okay? So the idea we can project V onto W, and you get a unique vector. When I say project, what I really mean is orthogonally. What I'm saying is there's exactly one place that you can drop a perpendicular, as you might say. Okay? This is a really important idea. Actually, where I drew it doesn't look right to me. I think I'd have to go down a little farther. But somewhere you can drop a perpendicular, and then what you get is you have kind of the component in that subspace. And so this is little w. And then the book will call this vector little w perp. And you'll notice that what we have is we have V equals little w plus little w perp. Where does little w perp live? Well, it lives in big W perp. And little w lives in big W in the subspace. So that's kind of the picture of the orthogonal decomposition theorem. Okay? It says that you can do this, and it says that you actually have a unique pair of vectors. There's only one choice for W. It doesn't totally show you how to find it, but we'll get at that in the next class, basically. So any questions on that so far? So that's the other, I guess, key factor is that the theorem says two things. Number one, this decomposition exists. And then two, it is unique. Okay? This is an example of what you call in mathematics an existence and uniqueness theorem. And I don't know if I want to go through the whole proof after break or not. I'm considering it. I have another activity I might do also. But this is very common in mathematics. You have what's called an existence and uniqueness theorem. First, you have to show that something exists, then you have to show there can't be another one. Okay? And that's the basic idea. All right. So I'll tell you what, guys. I think I'm going to pause for now. Let's take our break a little bit early. Yep. So let's see. Group work 3, find the error. It says, let's consider this subspace x minus y minus z equals 0. That's a plane through the origin with normal vector 1, -1, -1. So what does it look like? Well, let's see. 1, and then -1, so that would be this way. And then -1, so that would be down 1, right? So it's like somewhere over here, right?
We can't see what
Oh, you can't see what I'm doing? Well, then that doesn't help. So I guess if this vector here is the vector 1, -1, -1, then somehow you can imagine being orthogonal to that vector. I don't know, there's some kind of plane here. And this would be my plane, W. Okay? And it says this plane is, so this plane again is x minus y minus z equals 0. Does that make sense, guys? And actually, I guess what we'd say, if that's W, then we could say that W perp is the span of this vector in R3, right? It's going to be this line. Because a normal vector gives you a line in 3 space, and the plane is also a subspace. Oh, by the way, you guys asked me earlier, what does this mean? Intersection? I should bring that up now. Intersection means try to find the things that are common to both sets. And you guys had a theorem in the book, or maybe it was a little part of a theorem, which said that W intersect W perp equals what? Yeah, just the 0 vector. So the only place that W and W perp have in common is that they both share the 0 vector. They're both subspaces, but that's the only vector that's in common. Okay? So let's see what happens with this find the error. Then he says, okay, is this true? That W is spanned by 1, 1, 0 and 1, 0, 1? Well, yeah, because both of those make that equation true, right? So you could graph 1, 1, 0. Where would that be? Well, I guess it would be kind of coming right out at me, right? There's 1, 1, 0.
Is this the group work or what?
Yeah, this is the group work.
For the back or?
And 1, 0, 1, I guess, would be kind of right here. I'll tell you what, those two vectors do not look like they're in red W to me. I don't like my picture. Don't like it at all. Well, I'm trying. Okay. By the orthogonal decomposition theorem, we can find an orthogonal decomposition of V equals 1, 2, 3. And so, yeah, you say, yeah, I know the theorem.
1, negative 1, 1, or what?
Where?
What do you have there?
I have 1, 2. I'm just reading the sheet a little bit. And so when you see this, what they're doing, okay, so you see this notation. The way you read this, guys, the projection of vector V onto the subspace W. By the way, this whole mess right here, I would say that is the projection of V onto U2. See? Because it's a scalar multiple times U2. And this is the projection of V onto U1. Right? So that's a fancy way of writing it according to what he says. So he computes W and W perp. And then he says take the dot product. And what's the problem?
U2 of V.
He takes the dot products of W perp with U1 and U2, and he says we're not getting 0. Anyone come up with a reason why? Maybe he did the dot product wrong? Let's see. If you take W perp, no, you're not going to get 0 if you dot that with U1. Yeah.
Is there something wrong with their definition for V onto W?
I don't know. They say W perp is V minus W. Actually, if you look at the picture I did earlier, let's see, we had a couple pages ago. Yeah, here's my picture of the orthogonal decomposition theorem. Yeah, W perp is just V minus W. That seems to make sense, right? W perp is V. That's actually how you compute it. First, you get the projection, W here. This is the projection of V onto big W. But then you get W perp by subtracting. That is how you get it. Let's compare the group work to like an example from the book. They must do an example in the book of this, right? All right, let's find it. We have orthogonal complements and orthogonal projection. Here we go. Don't they do an example of the decomposition theorem somewhere? Yeah. There's a nice picture. Let's see. No, I went too far. Yeah, so I think the example before this is okay. They say, look, here's P. It's P1 plus P2. Yeah. So in their picture, the vector V goes down to a vector P. Ryan, go ahead.
I just figured it out. It's
You-
because you can't go and make V can't be 1, 2, 3 because you're not going to have the top number be 1 when other numbers are larger because of the two U's that you're working with. Like when you add those together, there's no linear combination of U1 and U2. Is that the reasoning why we're having this?
I don't know. I don't quite understand what you're saying.
I don't know, I think I know what you're saying.
You can't make this.
Yeah, you can't, he's saying there's no linear combination of U1 and U2 to get V.
Oh, no, but there doesn't have to be. if you look at this picture here, right? But you're starting to get somewhere. You guys are starting to get somewhere. Look at U1 and U2. What are U1 and U2 supposed to be?
It's supposed to be independent.
What's the theorem say? Let's look very carefully at what the theorem says. Let's see, it's on the next page. Orthogonal decomposition theorem is on the bottom of page 384. Okay, let W be a subspace, let V be a vector, then there are unique vectors such that this happens. I don't see any U's yet. Oh, but when you look at the proof, that's when they start talking about the U's. Proof. We need to show two things, that a decomposition exists and it's unique. Look at the first thing they do, guys. To show existence, we choose an orthogonal basis for W. Okay, see that? Look at the group work. What do we not have? It's not orthogonal, right? How do I know this is not an orthogonal basis? Yeah, if you did, right? If you took the dot product, what is U1 dot U2? It's 1. And what this shows you is the value of an orthogonal basis. We have this theorem that is really nice, but it only works if the proof only works if you have an orthogonal basis. Matter of fact, the picture only works if you have an orthogonal basis. Look at this picture again that we had on the previous page. You see vector P, which is the projection of vector V? P is equal to the sum of which vectors? P1 plus P2. But that only works if P1 and P2 are orthogonal. I guess I'd like to show you a picture where that is not the case, because I think that would kind of say something here, you know? So here is I'll try and draw a bad picture. A bad figure 5.8 would look like this. Here's W. And then they had a vector V. So there's vector V. And they want to project it onto W. And they're going to call that P. But suppose your basis for W is not orthogonal. See that? Now, if this is my basis, then my graph paper would look kind of like this, right? I mean, you'd have these parallelograms for graph paper. You've seen that before. I've done that with you guys. Okay, well then, if you were to drop your perpendicular to the first vector, or you drop your perpendicular to the second vector, it's not true that adding P1 and P2, that's not going to give you P anymore. The only reason that works is if your basis is orthogonal. Right? Because right now, if I added P1 and P2, I'd be out here somewhere. Because they're not orthogonal. I wouldn't be right under at a right angle. I'd miss. Does that make sense to you guys? So, and kind of show you where this is heading. What we're going to study in the next section is how you come up with an orthogonal basis. You're given some vector and you want to kind of break it down into its orthogonal components. But you need to have an orthogonal basis to start, or it just won't work. So I think that's kind of the point of the group work. Suppose W is this plane, x minus y minus z equals 0. And let's let v be the vector 1, 2, 3. Let's find the projection of v onto w the right way. Okay? So let's try and figure out what you should get when you project. Okay? So I guess the first thing is I need an orthogonal basis for W. So let's take U1 equal to 1, 1, 0, just like they did last time. I know I shouldn't take U2 equal to 0, 0, 1, right? Does anyone have something I can use for U2? Tell you what, I'm going to pause for a minute and see if you guys can think of what we might use for U2. I will do this. I'm going to call V the vector 1, 0, 1. Now we're not supposed to use V, right? Let's draw a picture of U1 and V. Here's U1 and here's V. Right? Not orthogonal because the dot product is 1. Okay? What I'm going to do next is this. I'm going to let P equal the projection of U1 onto V. Question, Jake?
Can you just like set up a system?
Maybe.
Because you can just do like x times 1 plus y times 1
Yep.
plus 0 times that exact. So then x plus y equals 0 and x minus y minus 1 equals 0.
Oh, so you have do you have an answer then?
Yeah, so I have a half, negative a half, and
1 half, negative 1 half, and 1. Would that work, guys?
Yeah.
I guess it would. I guess it would. So you got that using a system of equations. Cool. Then I'm okay. Then I'm okay. I want to show you the other technique I was starting to show, though. I think it might be smart.
What's U2 of 2 in this case?
Well, Jake came up with a half, negative a half, and 1. That's what you got, Brad?
I mean, I multiplied by 2.
Yours was 1, negative 1, and 2.
Yeah. I think you'd also have anything for the last one.
Oh, yeah.
Multiplying by 0, so for the third number, you'd have 0 if you want.
Oh, but interesting, though. If you make the last one 0, then it won't be a basis because they'll be linearly what? Dependent. Yeah. So you could, but you don't want to, right? But these are both good choices. Okay. So, but what I'm saying is the strategy is this. I'm going to let P be the projection of U1 onto V. So guys, P looks something like this, right? Like if you drop a right angle, this is P. You guys with me on that?
Mm-hmm.
And then, oh, I did it wrong. I don't want to do that. Shoot. That's not what I want to do. That's not what I want to do. What I want to let P equal, I want to let P equal the projection of V onto U1. That's what I want to do. So let's draw the picture again. Okay, so where are we at? We have U1 and V, right? Since I'm going to be projecting onto U1, here's U1, here's V. So the projection is going to be right here. That's P. Are you with me? And then I will let W be V minus P. So isn't that right here? There's W. Okay? And I'm going to set U2 equal to W. Make this my U2. Because then what'll be true? It'll be orthogonal to U1. Do you guys understand the picture? I'm telling you that this is the basic idea. This is the idea behind what is called Graham-Schmidt orthogonalization. And this is what you're going to read about for Thursday, section 5.3. That you drop a perpendicular onto the vector you started with, and then subtract, and then you get something that's orthogonal. So we'll go over more examples next time. Nice work today, guys.